Hi, everyone. Thanks for coming, and thanks for giving me this chance to talk about generative AI in AI PCs. This is an incredibly exciting space. I mean, this is an industry with over 1 billion users, so if you want to talk about the impact to our day-to-day lives, whether it's at work or if it's about just making more time so that we can have that time to spend with our families, I think that is going to happen right here first in our industry. So I'm excited to share some insights and some vision on what AMD is bringing to this generative AI space. A little bit about the work that I do at AMD. So I lead a team of AI developers that work directly with our partners, our customers, and software developers to bring some of these innovative solutions to bear on AI-enabled PCs. So I think the most exciting part about my job is I get to watch two evolutions happening at once. Like on one side, I get to watch the amazing engineering that goes on inside of AMD, both the software development teams as well as the silicon that's being enabled for these types of use cases. And on the other side, I'm working directly with the customers that are building this innovative solutions and this mind-bending rate of change of AI. And if you look back just in the last 12 months or 18 months, we've gone from models that process speech and text and video to models that generate speech and text and video. And that is a pretty mind-bending shift. And as you heard today from many of the innovative speakers, this arrival of Agentic AI has changed things quite a bit. You're now seeing more complex model architectures. You're seeing model pipelines that are changing dramatically in their underlying architecture. And with the agentic applications, you're seeing a lot more complex decision-making and task-based execution happening. And so that lends a really interesting and exciting problem for the technologies. And it's not slowing down. As we look forward to the next generation of applications, we can expect to see more of this multimodal input and output taking precedence in these applications and moving more towards a realistic reasoning aptitude within these devices, using multiple forms of inputs to generate multiple forms of outputs on our own behalf. And that's pretty exciting. So if you think about that in consideration of what's driving the design points for silicon and software solutions, it's interesting because certainly the computational requirements are going up. The complexity of the tasking and the decision-making that happens is also increasing. So faster and more processing power is important, but also the types of processing that is happening is becoming more diverse. And so what I'm excited about Ryzen and the client AI PC space is that you have this aptitude of different types of processors right here inside of the device. But the other thing to consider is that we are power constrained on these devices inherently. And so all of this has to happen by also considering efficiency as a #1 priority. And otherwise, we're not going to be opening up the aperture on these new use cases that are emerging in the device. So this third generation of Ryzen AI that Lisa talked about is a really exciting device because it's this convergence of some of the best IP in the world. You've got these 12 highly flexible, multi-core, multi-threaded processors that are going to be critical for the types of multitasking, decision-making, and parallel processing execution that we heard about today. You have 16 powerful RDNA 3.5 cores that are incredible parallel processors and embedded within the graphics pipeline itself. And then you have an XDNA 2 core, which is a neural processing engine that has industry-leading efficiency and performance. And so what Ryzen AI is bringing to the table is this unmatched performance without sacrificing the efficiency that we've held for multiple generations. So I'm going to start going deeper into the software stack, and I want to set the table and talk about the criteria for building a software stack has to consider 3 real fundamental things. The first is, and we heard about today, we have to think about how we engage the open source ecosystem. That is a critically important mandate within AMD. And as you can see, this is where a lot of innovations are happening. And that's more than just the frameworks. A lot of the optimizations are happening in the open source ecosystem. A lot of the quantization techniques are happening in this open source ecosystem. So we think about how we bring that into the tool set. Secondly, we need to provide the device-aware tools that allow our developers to customize their models within our own toolbox so they can provide the most differentiated and optimized solutions. And then thirdly, we want to be able to deploy with great flexibility onto this multiple processor environment with the greatest of ease in the runtime environment. So I'll click a little bit into tools that are specific to AI developers. And what our customers have told us is they want more insights. They want to understand, as they're innovating on these models, how are those going to fit into these different processors? How are they going to map to the device? And so what we're doing is we're providing tools that give them insights into graph-level analysis, tensor-level analysis, or even op-level analysis. And then we're also providing tools that let them track and audit and then tune their performance from iteration to iteration. And so some of those tools are shown here. And before we go deeper into the tools, and I'm going to show a few examples, I want to stop for a minute and talk more about this neural processing engine. And this is so important to our strategy, and it's so important to these AI PCs. And I want to point out a subtle trend that's happening, and it's more than just the performance. Now, certainly, if you look at all of these applications, whether LMs or stable diffusion, yes, of course, we've seen the charts. The models are growing in size. The computational power is increasing in size. The efficiency is very important. But one of the considerations is that all of these models are becoming more increasingly real-time. So we have models that are going to be executing for longer durations, and we have models and use cases that are going to be wanting to run all of the time or continuously while we're working on the system. And so that increasingly real-timeness is something that's uniquely driving the neural processing unit. But there's another subtle characteristic of the NPU that I also want to highlight. And as we think about some of these agentic workloads and the more complex pipelines, we need to think about more happening at the same time in the system. So it's no longer a matter of just running a model one time. We saw examples earlier in SGLang where you have many parallel processes happening at the same time. We also have to think about different types of workloads that are running at the same time. For instance, you could have a background processing application that's just constantly indexing all the new data that's coming into your system. You may have an LLM that's demanding in a human real-time type of time frame. And then thirdly, you could have your Microsoft Teams or other types of frame rate type of experiences that are running. And all of these things are running at completely different QoS domains. And so we need the separation of those multiple tasks that are happening simultaneously. And so that is a unique characteristic of the NPU spatial architecture within the XDNA architecture that we built. That spatial configurability allows you to pin resources into physical domains without having to time share that resource. The efficient multitasking comes from not having the context switching overhead that's predominant when you start time sharing that same resource. And then ultimately, the performance segregation is this idea that is still quite emergent in AI on PCs, and it's this idea of QoS, and how do you define and create and then incubate these different QoS domains? And that's an incredible, important consideration. So let's take a look at a quick demo. In this example of multitasking, we have a couple of applications we're going to fire up. On the left, you see Stable Diffusion XL. And this is a very computationally demanding application where we're generating images. And you can see in the bottom right, the NPU is firing up and is taking on that load. But maybe we want to run another application. Our friend is there waving to us who's going to turn on some team effects. And so now we're also activating things like background blur or face detect or hand tracking. And so in this case, you can see the NPU also taking on that workload. And as we launch the Stable Diffusion image generation, our performance hasn't been affected significantly. And that's interesting, because if we take a look in our analysis and our studies of other architectures, we just don't see that same type of benefit showing up in other neural processing units. Now, of course, nobody's immune to the effects of reaching into the disk drive or having to share memory accesses, and there's other system-level considerations. But in our studies, the impact on our devices is fairly minimal. Whereas if we study that same type of approach, even using a lesser computational model like Stable Diffusion 1.5, we see significant degradation in the competition. So we think this is a unique value in the Ryzen AI NPU architecture. So let's go back to software. I'm going to use GPU workflows as an example. And this is a really good showcase of how we're bridging the worlds between the innovation in the open source and the innovations within AMD's vendor software stacks. So one of the dominant activities in generative AI, whether it's stable diffusion or language models, and is this idea of device-aware optimization. So things like KV cache, which we heard about today, or different methods of fusion, even quantization methods, which are device-specific if you want to take advantage of int4 or block floating point 16. These types of innovations are happening in the open source ecosystem. And so we want to be able to tap into those and then augment them with our own tools to provide more vendor-aware and device-specific optimizations. And that's precisely what we're doing in this GPU workflow. Now, in the runtime environment, we're taking advantage of more industry standardization around DML and the Onyx Runtime. And that's critically important in the AI PC for software developers that want to take advantage of what's already deployed out in the Windows operating system. So let's take a look at another example. Let me walk you through another emerging software development flow around LLM specifically. And this is called Onyx Runtime Gen AI. And this is something that we're increasingly contributing to and leveraging for our LLM applications, both on GPUs or NPUs. So this is a great example where we've reached into the open source, places like Hugging Face, where we can easily access pre-quantized models and pull those into the system, leveraging Onyx to do model conversion and export using Model Builder as a primary flow. And then leveraging our own device optimization features and techniques to do device-specific optimizations, finally ending up in the runtime. Now, what Onyx Runtime Gen AI does is provide an industry standard way to easily distribute or put into production performant LLM solutions with APIs specific to tokenization, detokenization, and generation of these LLM models. So it's giving us that ubiquity across our device portfolio within Ryzen AI, and something you'll see us increasingly contributing to in the open source. So now let's take a look at that demo. So this is a really good example of the benefit of working in that open source space, is that it gives us that day zero readiness of very popular models as they're emerging. So this is an example of very recent Llama 3.2 model. I think this is a 1 billion parameter model integrated into one of our software vendors. This is the LM Studio application on day zero. So when that model came out, we were able to leverage that infrastructure to deploy this very quickly and launch that solution. So what you saw was them through the UI loading a pre-quantized model from an open source repository, firing it up in the tool, and immediately chatting with it. And this latest model lets us take advantage of the quality and the performance of the latest innovations in the space. And you can see this is extremely fast. I mean, this is a mind-blowing speed. But what that means is more speed means, well, we want more, right? So as models become increasingly more capable and more performant, we want to do more with them. And Agentic AI is a really great example of what's happening. And that is very present in the AI PC space. So we demoed this at Ryzen launch earlier in the summer, and we showed the transformative experience of being able to set off an agent to go index a YouTube video, pull that into your local embedding table, and then to be able to reference that information. And so what's interesting about Agentic AI is not just that capability, but as we think about the heterogeneous impact into the device. So within Agentic AI pipelines, we have RAG. So depending on your use case, RAG could easily deploy on a CPU, a GPU, or an NPU. For instance, if you have information that's coming in one time, your CPU could easily handle that task offline and then embed that information for your later retrieval. If maybe that data is real-time and coming in and you're willing to stop your process to quickly index that model, a GPU could do that quite performantly. And then thirdly, if you have tons of data coming into your application and you need all of that content to be continuously indexed and ready for your later retrieval, then an NPU is an excellent device for that. And so you can see how the use cases are going to warrant different types of flexibility and different types of deployment. And that's a key consideration in this type of solution. So there's one more example that I want to highlight that we've been working on this year, and that's in image generation. And this is another great example where the models are changing so quickly that it's not just the size of the model, It's the complexity of the pipeline, the number of encoders, the size of the VAE decoder within the pipeline. The core latent computational element itself has changed fundamentally in the last 12 months, from CNN and UNet style approaches to more diffusion transformers. And so what that means as a developer, if you want to keep up with this, you need a couple different strategies. The first is you need to move quickly and be able to explore that design space. And that's what we did within our own engineering teams, was look at the trade-off space between performance and efficiency and latency, deploying onto the GPU or shifting part of the pipeline onto the NPU, and then ultimately arriving at the most optimal solution. And so that was part of what we demonstrated a few slides earlier, was that final product. And so the second part of our strategy is to indeed take those final optimized solutions and then push them back out into our developer community, so developers have A, the flexibility to explore the design space, and then B, to leverage the most optimal solutions into production. So I'll wrap up by just highlighting a few key points that hopefully came across today. The first is that the developer tools really need to shift along with these emerging use cases. Not just the point tools that we use to analyze models, but the tools that we're building to help developers design, explore, and find what is the most flexible, fastest time to market, and optimal solution. And then to build those optimized solutions, we want to be able to push this back into the open source community, push the models into the open source as well so that they're easily available. And then last but not least, of course, you have to have this device leadership for generative AI, which is more than just peak tops or a peak spec on a data sheet. It really is about that diversity of processing elements within the device and being able to leverage them for your unique application. So thank you for letting me share some of these insights on these applications with you today. I've put some resources here. If anyone wants to try some of these demos or download some of these reference solutions, those links are provided here in the documents. I think these will be provided offline. And if anybody has questions for me offline, please just grab me afterwards. I'm happy to chat and take them. So thank you very much.